All right. So you didn't bring any gifts today? Well, last time you showed up to class, you had cupcakes. Now you've set an unrealistic expectation. All right. So let's pick up where we left off last time. We had finished talking about the CPU, how it's kind of the central component of our computer that knows how to do a bunch of magic tricks. Let's see what we were doing before that. Okay, and then we started talking about different kinds of programming languages, and we have the first one is machine language, the zeros and ones, and we talked about that's not really human-centric. We don't want to have the little two-button keyboard because it's A, error-prone for humans, right? We don't have that kind of attention span. And B, even if we did, it would take forever to write any programs, and we wouldn't have software because people would just give up on it, right? So even if we had the attention span, that wouldn't work out. So then we have this thing called a low-level language. Now these are generic qualifiers. We'll talk about examples of each of these types of languages, but we have this classification of programming language known as a low-level language, where every line of code, whatever that means, that we write in a low-level language, it translates into exactly one instruction or one magic trick that the CPU knows how to do. Okay? So this is going to be more English-like, so less of that tedious zeros and ones type thing. We can low-level languages utilize the entire keyboard, and we get to type commands. But it's still going to have the tedium of having very long programs. Okay, these are used sometimes. We'll talk about that here in a minute. But important thing to get out of this: low-level languages have a one-to-one relationship with the CPU. Okay, now we have our high-level languages, and these are the ones that human beings like. This has a one-to-many relationship with the CPU. So we write one line of code in a high-level language, and it translates into a lot of instructions, a lot of magic tricks that the CPU does. So we push one button, and a whole bunch of crap happens. Okay, that's the one we like. Now, in terms of when low-level languages are still used, and I would say every year they're used less and less. Let me just kind of talk about this in terms of the video game industry. I'm sure nobody in here plays video games, so it's probably not that important to you, but most of our video games today are probably written in C++. Maybe some of them are written in a language called C#. Both of those are high-level languages. And we're going to talk about another, in fact, why don't we just go ahead and talk about that now. There are two kinds of programming languages. And notice the previous slide said there are three types. We'll say types here just to keep it nice and confusing. Okay, so this slide said there are three types of programming languages. Next one says there are two types of programming languages. The two types of programming languages in the context of this slide are interpreted languages and compiled languages. All right, let's talk about compiled first. Okay, a compiled language uses a tool known as a compiler, which translates high-level code into its low-level equivalent. Okay, and maybe the kicker here is prior to runtime. Prior to runtime. So runtime being when you actually start the program, hit play, whatever. So before the program even starts running, this translation has occurred. Okay, so we want to think about compiled languages as being higher performance languages, faster. Okay, alternative is an interpreted languages uses a tool known as an interpreter, which translates in real time between the high-level code and another high or low level language. So in this case, the interpreter itself is a running program. You're not talking directly to the CPU in interpreted languages. Your program is talking to an interpreter, which is talking to something else. The interpreter is likely a compiled language, or is written in a compiled language, which then talks to the CPU. Important thing to get out of this, out of interpreted languages, is this guy is slow. This guy is fast. At least relatively speaking. Okay? So, none of us like slow, sluggish video games. So we're probably, if we were picking a language to write our video games in, we'd probably pick a compiled language. All right? We'll talk a little bit more about that in a second, but just to support what I was talking about in the previous slide. So we have this tool called a compiler, which translates a high-level language into a low-level language. Okay? So we write it with our power tool. So fewer lines of code equal lots and lots of magic tricks. Then we send it into the compiler, and the compiler turns our high-level code into the equivalent low-level code as if we had written that low-level code ourselves. So we get to write our code in high level, our video game in a high-level language, which has fewer lines of code. And then this specialized tool, the compiler, turns it into the low-level equivalent so that we didn't have to write those thousands of lines of code ourselves. Okay, we wrote 100 lines, it turned it into 10,000 lines, something like that. Okay, now, the quality, though, of those low-level lines of code produced by the compiler is at the mercy of how good the compiler is. So, over the years, compilers keep getting better and better and better, so they make us look like better programmers. In fact, you could make an argument today that you could write some pretty crappy high-level code, and the compiler might actually make you look better at the low level. It fixes some of your stuff, makes it more efficient, things like that. But let's assume, in our example, that people who are writing our video games are talented and pretty good high-level programmers, writing good, solid code. They're then sending it into the compiler, which is translating it into a low-level language, which has this one-to-one relationship with the CPU. Well, the output of the compiler, the low-level language, may not be as efficient as it should be for that game. Okay? And generally speaking, this isn't a problem. But we've had, if you're playing video games, how many of you are PC gamers? You use your computer for gaming. Okay? Xbox, PS3, the console, or Xbox One, PS4, if you're on the new gen consoles, you're at, that's a fixed feature set, right? Whether you bought it today, you bought it 6 months from now, it's going to have the same processor, same graphics card, that kind of crap. So all games are made for just that. So now, those of you who are PC gamers, how many of you built your own gaming rig? Okay, so you spent a lot of money, thought it was really cool, built a tower, probably had at least 2 monitors, spent a lot of money on your graphics card, right? Okay, anybody have what they think is a really good graphics card? Nobody wants to admit to it because I think I'm going to embarrass them. So you can go out. What's considered to be a pretty expensive graphics card if you're buying one of these, building one of these computers today? $600-700, $800. Okay, I mean that's not an unrealistic number just for the graphics card, right? I mean, you can even spend over $1,000 on a graphics card. But let's just say you spent $800 on a graphics card. A lot of us have computers that we didn't even spend $800 in the first place, unless it's a Mac, and then your default is $1,000 or more, right? So you go out and buy this great graphics card. Any of you have a graphics card that costs more than $400? $200? All right, we got $200. Decent graphics card, right? How many of you know how many frames per second you get on your graphics card with the game you play? What do you get? 110 frames per second. What game? Crisis? Oh, actually, Crisis from that's been out for what, about 2 years? 2 or 3 years. I remember when Crisis first came out, and this is kind of an interesting backstory to how games are created. Games typically take 2 or 3 years to write. So when you first start writing that piece of software, you have to aim it for what you think technology will look like in 3 years. And Crisis missed that by a little bit. They wrote the game to work on hardware, to work best on hardware that didn't quite exist when it came out. So when Crysis first came out, everybody had to turn all the settings down to be able to even play it. Okay, so decent example. So you're playing a game called Crysis. You get 110 frames per second on your graphics card, right? How many frames per second do you think the human eye can see? Not even 60. About between 35 and 40 frames per second is what the human eye can detect. Okay? Why the heck does he need 110 frames per second if we can't see any more than 40? Now, let's say you had one of these $800 graphics cards from today. How many frames per second do you think you could play that 3-year-old Crysis game? A lot, right? It wouldn't be 400 frames per second potentially, right? Is that worth $800 to run something at 400 frames per second when our eyes can only see 40 frames a second? So why should you ever get a graphics card that can't do, for the game you want to play, that can do more than 40 frames per second? Go ahead. Okay. Smoother in what way? You're right. At least I think you're right at this point. Okay. Now, generally speaking, when you're playing your game, you only see a drop in your frames per second in certain places, right? When you're in a portion of the game that has a lot of explosions, or if you're playing like an online game with a lot of people online, if you're in a city that has a bunch of other players on the screen, so there's a lot of things moving on the screen at once. If your frames per second it was at 110, you might see it drop to 60 in that one area, right? So what we do is, with graphics cards, we go for overkill, right? Let's do 400 frames per second so that when we're in a worst case scenario, we still get 200 frames per second. And in 2 years, when the newest, latest, greatest games come out, hopefully it still gets above 40 frames per second in a worst case scenario. It's kind of the punchline. All right, well, this low-level language idea, some parts of that game need to be really, 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 really fast. Okay? And this is more back on the CPU level rather than the GPU level. GPU is the graphics processor. So the CPU for the graphics card itself, which makes stuff show up on the screen. But some parts of that game need to be really fast. Now, we'll see in here that when we write our programs using GameSalad, we're going to have conditionals. We talked about that last time, right? We're going to be asking questions. We're going to be remembering things. We're going to be repeating stuff over and over again. Now, we know that there are situations, well, we can at least consider that there might be situations where a programming language may require us to ask a question in order for it to structurally be correct. But maybe we happen to know that that question is a waste of time. Let's say that you're solving a problem at home and you happen to know that you will never run out of something. But you still need to, if you were solving the problem, if you were writing generic instructions for this, you still need to make sure you had enough cleaner. Let's say it's cleaner. And let's say this cleaner automatically gets refilled and you know it's 100% filled all the time. Aren't you kind of wasting your time asking whether or not you have cleaner? Okay. Yeah, I'm forcing the example a little bit here, but let's just assume this is the case. Well, when that programmer writes the game in a high level for certain parts of the game, they might be forced into, because of the constraints of a high level language, into asking a question. Then it gets translated into that low level language, and the low level language is going to have the the equivalent question code. You might then go in and edit that low level language to remove some of the question portions so that it just executes assuming everything's fine. Something you wouldn't have been able to get away with at the high level language because the compiler would have yelled at you. Okay, the compiler has to be written with some structure in mind. So it's going to make you follow a very, tight-knit set of rules. But once you get into this low-level language where everything the CPU just says, okay, you want me to do this? This is my equivalent of that. You want me to do this? This is my equivalent of that. Once you get to that point, if you can go in and edit the low-level code, you can maybe increase the speed of certain portions of the game. Okay? Now, having said that, Humans will rarely use low-level languages today, much more often years ago because, as I said before, our compilers have gotten really good. But it's still possible that somebody's writing the latest, greatest game today, and when they compile it, a certain portion of the game doesn't run as fast as they would like it to run. And they may be able to go in and edit the low-level output of the compiler. Remember, the compiler is converts our high-level code into low-level code. So after we compile it, we can go in and edit that low-level code, just a little portion of it. So we're not writing the whole program in that, but we're editing just a piece of it to make it a little bit faster. Does that make sense? In fact, some of our modern languages, our modern high-level languages, actually have special tools or special syntax in them that will allow you to say, don't compile this portion. Here is the low-level language I want you to just pass through. So you're basically taking the effort off the compiler and just saying, don't compile this portion. This is what I want you to insert in the list of low-level instructions. So we'll actually allow you to embed your low-level code in your high-level code. But we're talking about really, really, really rare circumstances here. Okay? So from our perspective in here, we want to understand machine language, low-level, high-level as being what humans like, high-level, what humans can do but don't really like, low-level, and that's why we have compilers. And machine language, we appreciate it that it's there. We know that Bender speaks that, but we don't want to ever use it. Okay? Bender is the Futurama reference if you missed it from last class. All right, so this slide, two types of programming languages. We have interpreted and compiled. So most of our video games are going to be written in compiled languages because all that stuff happens before the game runs, which means that it's already in its most basic form when you start the game up so that it can just start cooking on the CPU. The speedier CPU just takes over and starts interpreting instructions in real time. Okay, going from one low-level instruction to the equivalent magic trick the CPU knows. So most of our video games will be done in compiled language. Now, there's a lot of applications that don't need to be super fast, right? Like, do you ever sit there, I mean, I guess unless your computer's really old, but are you ever impressed how fast Microsoft Word runs on one machine versus another? Or how fast QuickBooks runs or something like that? You know, pick some business application. You know, your machine's either too old or those things run at what you would call full speed on a whole wide range of computers. Whether you have a $300 graphics card with the latest, greatest CPU or the Best Buy budget pleaser from last year. Microsoft Word will run just fine. Although I do think it takes a little bit of time to load. Haven't you noticed that with Word? That doesn't make any sense to me. But regardless, that's even on fast computers. Something that Microsoft was doing there probably is fishy. But in any case, for business type applications, an interpreted language might be okay because we're not paying attention to speed like we would be in games. Interpreted languages are relatively slow compared to compiled languages. But our computers are pretty fast today. So even an interpreted language is going to be fast compared to people, right? We use computers as power tools that allow us to do a lot of things very, very quickly, where if a human being were performing those tasks, it would take us forever, right? So we can go and get a $300 or $400 budget pleaser computer from Best Buy, and that computer will let us do 90% of what we need to do, even if all the applications we're running on there are interpreted. In fact, how many of you have a Chromebook? Or know of a Chromebook? Okay, Chromebook computers, they're actually, basically it's an internet computer. All your applications run inside of a web browser. That's a program that's interpreted and then interpreted again. So those of you who have used a Chromebook before, don't they seem pretty fast? I mean, heck, you could play Angry Birds in there, right? So simple video games will work fine through interpreted stuff. Why is that? Our computers are really fast. All right? Those of you who built a new computer, let's see what you learned from 175 or Maybe let's see what Professor Wall taught you at 175. Some of you, a lot of you are in 175 right now. All right, this will make you look smart. Okay, so those of you who have built your own computer, which you will do in 175, that's one of the portions of the class, you'll build a computer. Where did you spend most of your money? So those of you who are gaming-centric people, those are the people who really make their own computers, right? Okay, so graphics card was probably top on your list. Had to make sure it was a good enough graphics card to play the games you wanted to play. Okay, what about after that? Go ahead. CPU. Oh, I'm glad you said that. Okay, can anybody tell me why he's wrong? See, that's what we get sucked into this thing that faster is always better, right? So you go to Best Buy, and have you ever seen at Best Buy they sometimes put giant numbers in front of things? I remember years ago when hard drives were first starting to be in the gigabytes. You know, you went in there and you wouldn't buy a 2 gigabyte hard drive. You would buy like a 2 billion bit hard drive. And they put all the zeros in there, and you just thought it was, well, that number of zeros must be better than this. It's a lot smaller number, even though you're not comparing apples to apples. But CPUs today, when you go into Best Buy, you go and buy a computer, you're looking at the different speed CPUs, right? 2.3 gigahertz, 2.7 gigahertz, 3.2 gigahertz. Then you have the other words after that, Core i3, Core i5, Core i7. What's good? What do you need? Why would you spend money on the CPU? I mean, obviously you need a CPU. So you can't just omit that part. You have to have that guy. But it's human nature for us to want a fast CPU, correct? Now, a lot of our CPUs today have multiple cores in them. What does that mean? They can do more than one thing at once. Well, what happened is we couldn't make CPUs any faster, so we just started putting multiple CPUs on one chip so that you could do more than one thing at once. Well, is more cores always better? How many of you ever had to choose between, when you bought a laptop or you bought a desktop, had to choose between a dual core and a quad core? And they talked you into the quad core because quad cores are faster. Ho, ho, ho. Nobody? Or are you just not admitting to it? Those of you who built your gaming computers, quad cores? All right. Did you even consider a dual core? How many of you went with AMD so you can get an octa-core? 8 cores. Why did you choose quad core over dual core? Not necessarily a bad decision, but why? Just did? Seemed better, right? Seemed better. Well, we can put this back into how human beings solve problems. What's the old joke? How many people does it take to change a light bulb? So we're going to have a light bulb changing contest. Okay? It's going to be me. And I'm very fast at changing light bulbs because I'm so tall. I don't need to have something to stand on typically. Okay? Against these 4 guys in this row. All right, we need a short row. Are you guys fairly? How tall are you? Can you reach the ceiling without standing on something? All right, we're good. All right, so this row, these 2 guys are going to race me in changing a light bulb. These are pretty high ceilings. I probably can't either, but let's just assume I can. Okay? Who's going to win? Let's say I can change the light bulb at a speed of 10, which is the higher the number, the faster. And each of you can change a light bulb at a speed of 8. We get 2 people to change one light bulb versus me, 1 person to change a light bulb. Who's going to win that race? I will. It doesn't take 2 people to change a light bulb. What are them going to be up there? Are they going to be fighting over who's going to be turning the light bulb the next time? Okay, light bulb is a one-man job, right? Okay. Now let's say instead we were picking up trash in a park. So now it's going to be me, and let's say I can pick up trash in a park at a speed of 20 against all of you. And let's say each of you can pick up trash in a park at a speed of 12. So you're a lot slower than me individually. But the park's a big place. Who's going to win? Who's going to pick up all the trash in that park more quickly? The group of people, right? So there's a problem that could be divided. The work can be divided up amongst multiple people, multiple cores. So when you get more than one core in a CPU, it's only going to benefit you in problems that can happen simultaneously. Okay, so that is more than one program opened at once, or in some of your games, you might have one portion of the game working on one core and another portion of the game working on another core, but at some point you run out of things that can all happen at the same time. All right? So for gaming, I would say quad core is probably the way to go anyways, but more cores does not always mean better. Also, faster per core. So when you get a 2.8 gigahertz Core i5 quad core, let's say, that is not necessarily better for you than a 2.3 gigahertz quad core Core i5. It's not necessarily faster. Well, what's that gigahertz thing? Well, at the same architecture, comparing Core i5s to Core i5s, that's the number of instructions it can do every second. How many billions of instructions can it do per second is what it really comes down to. Having said that, a faster processor only helps you if you're actually running out of time on your CPU. So if you are doing something that's so processor intensive that your CPU becomes the bottleneck, then you need a faster CPU. Interesting fact is your CPU sits completely idle, doing almost nothing about 97% of the time. 90% of the time, your CPU literally does nothing. You're only using it at all 3% of the time. And during that 3% of the time, you're probably not using the full capacity of that CPU. Some applications you might be. Gaming pushes the CPU pretty hard. So maybe a faster CPU makes some sense in gaming. But as fast as our CPUs are today, I doubt very much you would see the speed difference in playing your game between a 2.3 and a 2.8 gigahertz CPU, even though you'll see a difference in your wallet when you went and paid for that CPU. So faster is not always better. Probably the second best place to spend your money when you're building a computer is RAM, memory. But not to maximize your memory, to get enough for what you need. Buying a computer today, I'd probably say get at least 8 gigabytes of memory. In fact, maybe just get 8 gigabytes of memory unless you know you need more. Those of you who built gaming machines, how many of you did 16? 32? I had a guy last semester had a machine with 64 gigabytes of RAM. The funny thing is, the people who are gaming probably aren't doing their homework anyways. They're just playing games all the time, right? So they really have one application running at any point in time. Their video game. Well, your video game is likely going to take up less than 8 gigabytes of RAM of memory at any point in time. You could actually probably get by with 4 gigabytes. But we'll give you 8. But you spent money on 16 because you just wanted to, because the gaming guys, when you go to your forums and they always list what their rig is like, right? I got this graphics card, or I got 4 of those graphics cards linked together, and man, you got systems like that where you get those $1,000 graphics cards, but they get 4 of them. It's $4,000 in graphics cards. They link them all together to quadruple the speed of what it can do, as long as you can do 4 things at once, because that's like multiple cores, right? But the human eye can only see 40 frames a second, so then it becomes extra funny. All right, so, and the thing is that gamers are typically going to replace their equipment before their equipment can't do the job anymore. So in 2 years, they're going to build a new gaming machine anyways. Yet they just spent all this money on a graphics card they never actually took advantage of. So it does make it extra funny. So after you've gotten your 8 gigabytes of RAM, next place is hard drive. The speed of your hard drive is what's important. How many RPMs, or if it's a solid state drive, what its throughput is, not the size of the hard drive. And if you've ever seen an example of this, if you've bought a computer or configured a computer online, sometimes, and the good example I've seen with laptops, you will see maybe the machine comes standard with let's say a 2 terabyte hard drive. So a laptop comes standard with a 2 terabyte hard drive, or you could upgrade it to a 1 terabyte hard drive. Or actually, maybe more, the better example today would maybe be through Apple. Let's say the machine comes standard with a 1 terabyte hard drive, and you could upgrade it to a 256 gigabyte hard drive for an extra $600. So you're going to get 1/4 of the total storage space for another $500 or $600. How's that an upgrade? Well, the storage space wasn't what you were paying for. Paying for the technology. Chances are the 1 terabyte hard drive was a 5400 RPM serial ATA hard drive, where the 256 gigabyte one was probably a solid state drive with no moving parts. So that drives a lot faster. It's like a sports car. It can go really, 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 really fast. It can't fit very many people in it. Make sense? Okay, so, gamers want fast hard drives. If you're building a machine today and you want the machine to have the highest performance, what you do is you get, even if it's not a gamer, you get a smaller solid state drive that you install the operating system on, so that when the machine boots up, it boots up quickly. And then you get a larger mechanical drive, like a 2 or 3 terabyte drive, who cares what the speed of it is, and that's where you install all your applications. Because all that happens is when you double click on Word, it launches and gets stuck into memory. You just want to use that big hard drive to store all your crap and your illegal songs that you're downloading. And now it's not just songs anymore, now it's movies, right? And video games, obviously. You probably, all the money you spend on your computer, you probably steal most of your video games, I'm assuming. All right, so interesting thing. You'll talk about that a lot in 175, but the connection here is this idea of interpreted versus compiled languages, that our computers today are really fast, even what we consider to be cheap computers. Just because something is a 2.3 gigahertz processor versus a 3.2 gigahertz processor doesn't mean we're comparing a bicycle to a Ferrari. We're talking about two fast machines, and only for very specialized purposes, only for certain applications, will that faster processor even benefit you. Okay? Similarly, only will very specific applications even benefit you from having multiple cores. Good example of that. For those of you who download perfectly legitimate, completely legal movies, right? So you get your 2 or 3 gigabyte video off the internet, and it's in a certain format. And let's say you need to convert it to a different format for it to be able to play in iTunes, or maybe you run it through your Xbox, whatever. You have to convert it to a different format. Anybody in here ever had to do that? Convert a movie? Sometimes that takes quite a bit of time, right? On a traditional machine. So if I was doing this on this laptop, this is a quad-core Core i7 laptop, considered to be a pretty fast laptop. Converting an hour-and-a-half movie might take about 15-20 minutes. If I were to go on to a dual-core machine, it would probably take about 40 minutes. If you go to a single-core machine, it would probably take about 3 hours. So now you start talking about if you're in the Mac world, the Mac Pros, the machines where you can get 2 quad cores or 2 6-core processors. You have 12 total cores in the machine. Well, that same movie you can probably convert in about 3 minutes. Because converting movies is kind of like that example of cleaning up the park. You can have each of those processors working on a portion of the file simultaneously. So if you're doing a lot of, for graphics people, if you're doing a lot of video rendering or rendering large images, working with a lot of bits, multiple cores helps. But then again, you might say, well, why do I need to buy a $5,000, $6,000 Mac Pro to convert my videos when I just download the video, set it to convert overnight while I'm sleeping, and I wake up and it's done? Who cares that it took 4 hours? 4 hours, 4 minutes, doesn't matter. I wasn't going to watch it till tomorrow anyways. The trade-off there. But you kind of see that these are application-specific type of discussions. All right, so punchline here being interpreted, I want you to think slow in a relative sense, though. Computers are really fast. Compiled, think about fast, again, relative. The other thing is, we're just kind of adding the other thing, so let's call this prior to runtime, add. at runtime. So an interpreted language is going to make those, and it's going to interpret the high-level code to low-level code while the program's running in real time. Where a compiled language will do that ahead of time. And a real-world example might be if you've ever watched, some sort of debate or presidential address where there's like an interpreter who's singing in another language at the same time or doing the sign language for it. There's a delay, right? President says 2 or 3 things. The sign language person is trying to keep up, or the person converting it to German is trying to keep up. That's kind of like an interpreted language, where there's an interpreter, and the people who are understanding it in German or understanding it in sign language are getting the thing slightly slower than it was originally delivered, okay? Because it's having to go through an interpreter for them. The compiled language, this is going to make more sense for the German version of this, before the president starts talking, his speech gets translated into German. And then the person who speaks German is just going to read it in real time in German. So he already has the words, he just has to say them, as opposed to having to translate them while the president's talking. That makes sense? So that's the compiled language. Interpreted language is having the interpreted. Okay, 3 types of programming languages, 2 types of programming languages. There are 3 types of programming languages. Functional languages, procedural languages, and object-oriented languages. Okay, so every one of these slides is kind of looking at programming languages through a different lens. Okay, so this one's 3 different types of programming languages: functional, procedural, object-oriented. Functional languages are languages where the features are provided as self-contained functions that often perform complex tasks. So all problem solving done in functional languages must be done in terms of pre-built tools. Okay, you don't get to go down to a very granular level. An example of this, for those of you who have a graphing calculator, probably a Texas Instruments graphing calculator, right? For those of you who have been in calculus classes and got one of the better graphing calculators where you can just put in the integration thing and then reverse engineer your work. You didn't know that, you can do that. So any of you taking calculus and you want to spend a little more money on the better the better graphing calculator that does symbolic integration and symbolic derivatives, if you ever get stuck on an exam or a homework assignment, well, more importantly on an exam, you can just punch in what the question is. It'll give you what the final answer is, and then you can reverse engineer your work. And hopefully somewhere in there you actually learn how it works. So I'm just trying to save you some points on an exam where you have a brain fart or something like that. So this isn't cheating. That's why the teacher wants to see your work. They want to see how you got to the answer. But to save yourself some points on a test, reverse engineering your work might help. But in any case, the Texas Instrument things, when you type something in there, you are solving problems in terms of the functions already built into the language the calculator understands. So you might say the sine of 45 plus the cosine of 30 plus 8. So sine and cosine are both functions that do something magical behind the scenes. It's a complex thing that's built into this module called sine or called cosine. And you just call upon that, providing it its input, and it magically does stuff for you. Okay? So functional languages have a lot of built-in tools like that. Generalistic programming in computer science or IT often does not use many functional languages. In fact, the idea between a functional language and an object-oriented language has become blurred over the years. true functional languages are very much what I've advertised, in that you solve all problems in terms of pre-figured out complex routines. Okay? Modernly, how many of you have heard of a language called PHP? Anybody know what PHP is for? Or you just heard of the language? Okay, PHP is mostly for developing web pages, for making dynamic web pages. So PHP would be considered a high-level language. It would be considered a procedural plus language. We'll talk about that in a few minutes. So somewhere between procedural and object-oriented. But realistically, it has a lot of features in it that are like functional languages because it has a whole bunch of tools built in for doing web stuff. Stuff that you often do when writing dynamic web pages. Okay? Which would be very much like how functional languages are set up. So they've kind of said, here's PHP, and here's a whole bunch of web crap that we've put in there as available functions for you to do stuff. But by the way, we're also kind of a general language over here that you could do some other things as well. Where a true functional language doesn't give you that much flexibility on the other side. Okay? So there is some blurry areas here. Generally speaking, I say functional languages are, from a traditional computer science perspective, not that important for you to understand. They're very specific to certain tasks. Most of the functional languages that are used today are used very specifically for like artificial intelligence types of applications. For those of you who are computer science majors, you'll eventually probably take the 470 class with me, which I would say is the probably is funnest a word? Most fun? Most funnest. Okay, probably probably my favorite class in computer science, and probably the class I think is the most fun. But you'll probably think of it as the hardest class you've ever taken. But we use a functional language in there called Scheme for writing our own programming languages. It's actually a really cool class. But in that class, we use a functional language so that we can focus on building programming languages rather than learning a new language, because it has a bunch of pre-built stuff. Okay, so that's our high level of functional languages. I likely will not ask you very many things about functional languages. It's kind of a tough concept to understand, and it really is fairly meaningless in today's world because so many of these things kind of mix together. Procedural languages. These are languages which tend to produce monolithic programs that are very let's say very linear in nature and expose many details. I'm actually going to go ahead and define object-oriented as well, so I can use an example for the difference between the two of them. So object-oriented languages would be languages which try to mimic the way humans really solve problems, where we think of things in terms of functional objects where the details are hidden within the objects. Okay, I'll give you the example of that in a second. I think procedural object-oriented will make sense. Okay, so even though we're all used to cell phones and stuff like that now, let's well, I mean, a cell phone's not a horrible example. Fine, we'll use a cell phone as an example. I usually use a normal phone, but cell phone. So everybody in here has used a cell phone, right? Some of us haven't probably made a phone call in a while, because now we just use them for texting and messaging and all that other crap. But does everybody in here feel confident that if I handed you a random cell phone that was unlocked, that you didn't have to put a password into or something like that, that you could figure out how to make a phone call with it? Whether it's iPhone or Android, whichever one you're used to, or it's something else, or one of the feature phones, we know enough about cell phones that all of us in here, through some fumbling, could probably get to the point where we can make a phone call, right? So as human beings, we think of a phone as being at least a minimal set of features. And regardless of how that phone was designed or the software in that phone was designed, through some fumbling, we can kind of figure out how to get to those basic features, right? All right, so when we look at that cell phone, this guy sitting here, I say, what is this? And you say, okay, that's a cell phone or a smartphone, whatever you want to call it, okay? You think of this as the object, a smartphone, even though you know there's a bunch of stuff inside of here that magically makes this work, right? We all believe this isn't just this solid object. There's stuff in here that a bunch of smart people made and mass produced that magically makes this thing do a bunch of stuff, right? But when we think about it in terms of it being this object. And we think about it in terms of its public interfaces. That is, so this is an iPhone. So I have a little button over here. So this is one of the public interfaces. So this is an exposed feature. I push that and something happens. I push this and something happens. I push these two buttons over here and something happens for volume control. Okay? And then I can touch the screen and stuff like that. So all my inputs that I do with this phone are done in terms of these publicly accessible interfaces. The couple of buttons that Apple has exposed to me, right? Similarly, those of you who have Android phones, every one of the Android phones has a back button, right? That's kind of a distinguishing feature between iPhone and Android, is that when you're in an app, the phone itself has a built-in thing to go back to the previous screen, where iPhone apps have to build that into them if that's something that makes sense for the app. So Android has that additional public feature, okay? But human beings think about the world around us in terms of these objects and what they can do. And we only think about the details inside of this when we have to. So if your phone is broken and you take it into a place to get fixed, they start explaining to you how the screen works and stuff like that. Sensor XYZ is broken behind the screen or something like that. Those are things we never really think about because we don't have to. Those of you who have a car, who've driven, you don't necessarily care how the engine works, you just care that it works. If you're a hobbyist, now you're interested in the engine, maybe you take it to the next step, but the point is, we had a couple people in here who've built their own computers. I bet we have a lot of people in here who've never built a computer, but they can still use a computer. The fact that they don't know how everything works inside, not a big deal. Until something happens that they have to pay attention to that, where they have to replace a graphics card or something like that, or put a new stick of RAM in, whatever. Okay, so human beings like the world in terms of objects. Okay, so the object-oriented version of a cell phone would be this. All the details are here. They're hidden from us. If we had to go inside and make some modifications, we could. But generally speaking, this is already created and functional, and we use it in terms of its public interfaces. Now, the procedural version of that cell phone would be you come in and there's just a whole bunch of wires piled on this table. Okay? And through some investigation, you find out that they're actually all connected just right, such that that is a functional smartphone. You find the touch screen somewhere in there, you find a couple of the buttons laying around, and you kind of hold the back a little bit so you can make the button actually depress. But through some investigation, you actually learn that that is a functional smartphone. But you see all these details over and above the public interfaces. That's procedural programming. All the details are exposed. Still solves the program of a smartphone. Solves the problem of a smartphone, what it's supposed to accomplish. Okay? But all the details are exposed, so we kind of have to fish through the stuff that's unimportant to us using that to get to the pieces of it that are important for us to use it. Object-oriented gives us a level of abstraction where the details are hidden from us, available if we need to get to those wires, but generally speaking, just to use the object, we have our nice buttons for the public interfaces. That make sense? So procedural is a little bit older model. More modernly, all of our languages are object-oriented languages, which allow us to build the tools, the problem-solving tools in our language, out of objects, where we still built those details in, but then we hid them inside of an object so we can just start using those objects to solve problems. Okay, just like a house where somebody built that house, put all the wires in the wall, and then put up drywall so we don't see them. Make sense? All right, I will see everybody on Friday.